All right, we are working on AA6b-3 modeling with exponential equations today. A lot of this should be some review for many of you, and then for others perhaps not. So hopefully we can get you comfortable with exponential equations before we go into logarithms, which is part C of chapter 6. First off, with the warm-up, as usual, what I would hope that you do before I go over the whole thing is I would pause the video if I were you and try the problems on your own. That way you can kind of see where your mistakes are and where if you made mistakes, and see where you need to improve so you can move forward from there. All right. So the first one, solve by rebasing, this is what we did last time, and rebasing is kind of just the phrase that we use for it. I'm not sure it has a technical term, and it has pretty limited use because it only works if you can change the base to have common bases. So what we're looking at here, those two, 9 and 27, those are our bases, and we need them to be the same in order to solve this, having not gone into logs yet. So 9 and 27 can both be rewritten so that they are that they have a base of 3. 9 can be rewritten as 3 squared, and 27 can be rewritten as 3 to the third. So if I rewrite this as 3 to the second to the x, so I just replaced this 9 with 3 to the second, and then I brought the x over, equals 3 to the third to the x plus 6. And then what I need to do, according to my laws of exponents that we worked on in 6b1, whenever I have a power to another power, I end up multiplying those exponents, so 3 times x plus 6. What's important here is we need to recognize that this is multiplied by the quantity x plus 6, so you have to distribute that. So once I have the same base, these are both a base of 3. Once I have the same base, then I can just set the exponents equal to each other because I don't have anything else going on in that equation. So this is just 2x equals 3x plus 6, 3 times x plus 6. I'm going to distribute the 3x to be 3x plus 18. Sorry, distribute the 3, not 3x. And then subtract 3x from both sides. So I've got negative 1x equals 18, divide by negative 1, running out of space, so x equals negative 18. And that's my answer. I'm going to move this up. Finding the equation of the line, we haven't done this for a while. It's actually an Algebra 1-2 skill. I just haven't seen it for a while probably. But I wanted to go over it because it's a skill you're going to be using today, essentially plugging in what you know and solving for what you don't. So a linear equation, one of the forms is y equals mx plus b. M is your slope, and b is your y-intercept. So if I take my slope of 3, that's what I'm going to plug in for m, and then I'm going to use the point that it's crossing through as my x and y values. So I'm going to set this up as 7 equals 3 times 2 plus b that I don't know. And then I just solve for b. So 7 equals 6 plus b. That looks like a 6. b minus 6 minus 6. I've got 1 equals b. So this equation then, y equals 3x plus 1. So that's the warm-up. So what we're getting into today is exponential equations and how they come together. So linear equations, when you have like an xy table and they go 1, 2, 3, 4 for x's, linear equations will go up or down by the same amount. So they might go like 3, 6, 9, 12. So that, in that case, they're adding 3 every time. It could be something that's subtracting 3 every time or whatever. With an exponential equation, rather than add the same amount every time, it's getting multiplied by the same amount every time. So let's say I multiply by 2 every time. So I start with 3, multiply by 2 to get 6, multiply by 2 to get 12, multiply by 2 to get 24. So the growth rate is not a constant rate of change. This is a multiplier, and that multiplier is b. And they can also go down. We'll talk about that in a minute. A is your starting point, which I didn't put on here, would be where x equals 0. So I'm going to get rid of that table. We'll talk about it more later. That was just on the fly. It didn't work out that well. A is your starting point. And more specifically, it's where x equals 0. And if you're looking at a graph, it's your y-intercept. Anytime x equals 0, that's your y-intercept. So that's the general setup. Y equals a times b to the power of x. And keep in mind, in the order of operation, anytime you're evaluating, you're always going to do the exponent first and then multiply that by your a. All right. So we're going to look at several different situations and how to model them. So the first one is probably the easiest of them when I know my starting point, because there's where x equals 0, so my starting point is 5. And then to figure out what my multiplier is, I'm going to look at, so something to consider is that as we're going down, this is multiplying by something every time. And it may be very obvious to you, or it may not be obvious to you. In this case, it's multiplying by 2. 5 times 2 is 10, 10 times 2 is 20, 20 times 2 is 40, 40 times 2 is 80. And to figure out what it is, if it's not obvious to you, you go back the other direction and divide. So 80 divided by 40 is 2, 40 divided by 20 is 2, 20 divided by 10 is 2, so on and so forth. So our multiplier then is going to be 2. So for our equation, we have y equals 5 for our starting point. I always put the multiplier in parentheses, so this is 2 to the power of x, and that's our equation. That's a situation where the money is doubling, which we also could have used to figure out 2, but the number 2 for our multiplier. Okay, so the first one, the money was doubling. We were looking at a multiplier that was a whole number. It doesn't have to be a whole number, but it does have to be greater than 1. We also have situations where the values are decreasing, which is called exponential decay. So 81 is reducing to 27, reducing to 9, to 3, to 1. But the process for figuring out what that multiplier is still the same. 1 divided by 3 is 1/3, 3 divided by 9 is 1/3, 9 divided by 27 is 1/3, so on and so forth. So again, starting point, we've got 81. So y equals 81 times 1/3 to the x. And these two situations are good illustrations of the difference between exponential growth and exponential. And then to decay, that number needs to be between 0 and 1. So I would put this down in your notes. For exponential growth, the multiplier must be greater than 1. And it can't be 1 because that wouldn't grow. If we just multiply by 1 every time, then it would just stay the same. Exponential decay, the multiplier, I'm going to make a note here, not including 1. For exponential decay, the multiplier must be between 0 and 1. So if we have b, it's going to be less than 1 and greater than 0. And certainly, again, not including 0 and 1, because if your multiplier is 0, everything's going to be 0, and if your multiplier is 1, there's just not going to be any growth. So that's the difference, exponential growth and decay. You've probably heard those terms in the science class before. Next situation we're going to look at is when we know the starting point and we know the next point. So they're consecutive and you have a starting point. So again, I'm going to take 24 divided by 8. That gives me my growth factor. I'm going to change to white there. So 24 divided by 8 gives me 3. So my B value is 3. So then my starting point, right there, where x equals 0, so y equals 8 times 3 to the x. So simple enough if I know the first 2 points. Next situation, I know the first one, but I don't know the one following it. So essentially, I'm looking at this in 2 different ways. I know my starting point, so one way to do this is you know A, you know an X, and you know a Y. So this is my X, this is my Y, this is my A. So if I plug all those things in, the only thing I don't know is B. So if I've got y equals a, I'll write that down, y equals ab to the x, I'm going to replace y with 10. I'm going to replace a with 50. Don't know my multiplier, so I'm going to leave that as b, and then I'm going to replace the x with 3. So then I just need to solve for b. So I'm going to divide both sides by 50 to get rid of that 50. Gives me 1/5, and we're going to have to work with decimals a lot today. I usually like to leave things in fractions and leave them in exact terms, but that gets really complicated, and I don't want you guys to get hung up on that part without learning the part you're supposed to learn. So 10 divided by 50 is 0.2, so that equals b to the third. So to solve for b, anytime you're solving for the base, you're going to have to take some kind of root. The other way to go about this with fractional roots, with fractional exponents is if I take the cube root of both sides, that is the same thing as, whoops, too far, putting both of them to the power of 1/3. 1/3, not 3. The reason that works is because I'd be multiplying these exponents, so 3 times 1/3 is just 1, so that's what gets b alone on this side. So over here I've got b, and then on the calculator I'm going to do 0.2 to the parentheses 1 divided by 3, and I wish I could figure out how to show you that, but so I'll put that down here. What that looks like in the calculator, 0.2 to the power of parentheses 1 divided by 3. That's how you would put that in. And you get approximately 0.58, goes 0.5848, blah, 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 blah. So 0.58. So now that I know b and I know a, I can write my equation. So y equals 50 times 0.58 to the x. Next section. I know them consecutively, but I don't know my starting point. And in some cases, you can just work backwards if you can figure out your multiplier, but in some cases, that's just not feasible. So we want to have situations where, or we want to have the skills to do either one. So first, we're going to start with b. b is going to be 60 divided by 40, which equals 1.5. And then I can pick any pair. I can either use this for my x and y, or I can use this for my x and y. It really doesn't matter. I'm going to go ahead and use the 3 and the 40. So 3 is x, 40 is y. Plug everything in that I know. 40 equals, I don't know the starting point. My multiplier is 1.5, and then my x is 3. So 1.5 to the third is 3.375. This is times a equals 40. I'm going to divide both sides by 3.375 to get rid of it on that side, or divide out to 1 more specifically. 40 divided by 3.375 is 11.85185,185. So I'm just going to round that to 11.85. Now I know A and I know B, so y equals 11.85 times 1.5 to the x. So that's when they are consecutive, but I don't know my starting point. Last situation, not on page, sorry. Last situation, you can use in any of the previous ones. You can use what I'm about to show you in any of those. You're essentially setting up a system of equations similar to how you would do if you were trying to solve for an x and y in a linear system. But since this is exponential, we're not going to add our equations, we're going to divide them. So we're going to use these as x and y for one of them and x and y for the other one. So what we're solving for is not x and y, but a and b. So for this one, oh, no, just kidding. I'm going to put the bigger exponent on the top, or the bigger x on the top. So I'm going to plug this into the y equals ab to the x. So 100 equals ab to the fourth. And then I'm going to take this one, I'm going to do 300 equals ab to the third. Then what I'm going to do is divide those two. When I do that, because all I'm doing is multiplying here, a and a divide out to 1. So that's how, oh, this was not to the third. I apologize if that was confusing. This should be to the second. A divided by a gives me 1. That's how a gets eliminated. So what I have here is 100 divided by 300, which is 1/3. And then here, I'm going to put off to the side b to the fourth over b to the second. This is the quotient rule. I'm going to subtract my exponents. So b to the 4 minus 2 equals b to the second. The reason I'm showing you this part is because when we write b to the second here, I don't want you to think that this was being dropped down. You have to do this part so that you know, to make sure you know what that is referring to. Okay, so we've got 1/3 equals b to the second. So then we're going to take the square root of both sides. So square root of 1/3 equals the square root of b squared. So b equals some awful decimal, 0.57735, yada, yada, yada. So I'm going to round that to 0.58. And as with any other system of equations, when I am working with this, I also need to figure out my other variable, which is a. So I'm going to take one of my starting equations. Let's do the 300 equals ab to the second. But now I know what b is, so I'm going to plug in 0.58 to the second. So then I do 0.58 to the second. I get 0.3364. 300 equals a times 0.3364. And 300 divided by 0.3364 is 891.795, so on and so forth. So I'm left with a equals 891 point, I'm going to round that to 8. And just an FYI, the rounding can throw things off because of the nature of exponential equations, can throw things off an awful lot. When in my different classes, when we rounded these in different ways, we ended up with starting values anywhere from 880 to, I think it was 920. So keep that in mind if you're looking at my key to your homework or anything like that. So our equation, y equals 891.8 times 0.58 to the x. And that's my final equation. All right, so that is it. You're going to have a test next class, and that will be covering 6A 1 through 3. That's the inverses, graphically, algebraically, and verifying and then 6b-2 and 3, which is the rebasing, which we talked about in the warm-up, and then what we just went over now. So that's it. You're allowed one side of a half a sheet of notes, and all right, have a good day.